I want to first establish my own position where I'm coming from so that those of you who don't know me will at least understand why I have taken the position I take. We're going to talk about looking for time in all the wrong places, and it's really the subtext is why real science really matters. And I want to start by looking at some of the things that science can't do, and this may surprise some of you, but this is something I learned about many years ago when I first came out here to graduate school and met with Dr. Leonard Brand and Dr. Bernie Neufeld, who had both finished their PhDs about the same time, and we sat down together to decide what to do with our lives, and one of the things we wanted to do was go solve the creation-evolution mess so that we could continue with our careers in molecular biology or animal behavior or whatever it was. So we were going to go do that first. And when we sat down to look at the possibilities, we soon learned that there are these two lists, the list of things that are problems for creation and the things that are problems for evolution. And we realized that we would never get anywhere by tackling the lists. This, for example, are some of the things that challenge the idea of a FIAT creation, radiometric dating, other dating methods, the fossil record, some aspects of the fossil record. And then there was the other list, which included things that challenged the evolutionary model, like origin of life, other aspects of the fossil record, the sudden appearance, the general absence of intermediate forms. And then there were things in sedimentology and catastrophism that have come to be on this list as well that we're going to talk about today. And then there was molecular biology. So all of these things looked like they were in the camp of creation, and the other ones looked like they were the camp of evolutionists. And so when you actually look at the data, you look at the physical data, you look at the empirical data, and you realize that what we see is something like this. It's not this that we might expect to see if we believe in creation, or this if we're evolutionists, but it looks like this. As a result of that, it's not higher math to realize that if you have the same thing on both sides of the equation, they cancel out. So for those who know the science, and this involves knowing all of the science, if you know the science, the decision about origins is always going to be based on something other than science. You can't use science to determine which of the models is correct. Having discovered this very early in our careers, we then began to figure out what we could do with science that would be very useful. As far as a rational basis, and coming back to Scripture, since we are here as a Sabbath school class, I believe in the biblical model of origins. The first 11 chapters of Genesis are to be taken literally, not because James Barr, the well-known, respected Hebrew scholar, says they were written that way, not because the Old Testament repeatedly refers to them as literal events, not because Jesus referred to Adam and Eve as real people, not because the disciples did, but because of Romans chapter 5. Romans chapter 5 has a very simple equation. It's so simple that you'd think speaking it once would be enough. It says, because, or if, there was a Garden of Eden with a perfect man who then chose to fall and perpetuated sin on us, if that's the case, then there was a man, Jesus Christ, who came and lived a perfect life and offers that life as a substitute for ours. If, then. Now, it's not repeated once. It's not just there once in Romans chapter 5. It's repeated 7 times. The same equation over and over and over again, so that nobody could come into judgment and say, well, I didn't understand that simple equation, Lord. It's there 7 times in that one chapter. So I would assume then, as a logical, rational person, that if I reject that simple equation, and if I choose to have a view of world history that doesn't involve a perfect garden and a perfect man, then I'm also throwing out the solution to that problem, which is the sacrifice of Jesus Christ on the cross. And I'm not willing to do that as a rational person. So that's why I believe the way I believe. What can science do then if it can't give us the solution to origins? We can investigate the natural world, which a lot of us take as our first calling. We can test ideas about the natural world to see if they work. And perhaps if you are successful as a scientist, if you publish papers and you do research projects that are successful, people may become interested in your other ideas. And I think Leonard Brand has documented that this has happened many times. Also, capping it all off, science is fun. My daughter says I've never worked a day in my life. And except for grading exams, I pretty much agree with her. All right, now let's take a look at time in the fossil record. The most common interpretations of radiometric data would take life on Earth far beyond the biblical time frame. Although progress is being made, efforts to resolve this discrepancy head-on have thus far not been fruitful. So we're going to take a look at some features in the fossil record which seem to contradict the conclusions of radiometric dating. If the deposition of sediments that consists of rocks around us occurred over millions of years, what features in the rock should confirm that? If the sedimentary processes were occurring more rapidly, how would we know that? About 15 years ago, Dr. Brand and I and several other people sat down and said, why don't we go look at the fossil record to see if we can find time? And that's why I titled my talk, Looking for Time in All the Wrong Places, as you'll see. So we set out to examine the rocks of the Colorado Plateau. Dr. Phillips down here and Rose Weeks have both been involved in this project, and numerous other people as well. And it's gone on for quite a number of years now. We chose the Colorado Plateau because it's nearby. That's good. It has a good climate, dry. Dry is good for geologists, by the way, because that's how you see the rocks. And the rocks are well exposed as a result. So we're going to look at 5 different issues unless we run out of time, and then we'll look at 3 or 4. Let's look at the first one. These are all issues that relate to radiometric dating indirectly and also relate to the rate of deposition. Sediments appear to have accumulated rapidly. When we examine sedimentary layers, one important question that we would like to answer is how fast did these layers accumulate? And as we try to answer that question, we come to the following possibilities. We can measure the rates in modern depositional environments. We can assume the rates in the past were similar and then get a rate based on these assumptions. So that's one thing we can do, is just look in the modern environment, see how fast things are accumulating today, and then ascribe that rate to the past. Secondly, we can look at some external standard or external information about past time and apply this to the sedimentary rocks. For example, we can find radiometric dates associated with certain layers of rock. Then we can measure the amount of sediment between those layers of rock, and from that calculate a rate. Or we could use the Bible. It's another external source that tells us that the Earth, the history of the Earth is reasonably short, and in fact that much of the sediment may have accumulated in 1 year. And we can determine a rate based on that. The third thing we can do is look at sedimentation itself. Determine how fast sediment has to be deposited to maintain the kind of deposits that you have in the fossil record. Let's take a look at the answers we get with each of these methods. Modern rates for sediment accumulation in depositional environments, such as here off the Mississippi and so on, give us rates in centimeters per year. Often these are a centimeter more or less. So here I have a time scale on the bottom in years. in centimeters per year. This is a rate. And 0, of course, is 1 centimeter per year. If we look at rates based on radiometric dating, this, for example, is the Moenkopi Formation, and it's supposed to have accumulated in 10 million years. That gives us rates that are off by 3 orders of magnitude. So they're much, much slower than any rates we measure in depositional environments today. That, of course, is a challenge to the method of deriving time, because I don't think the sediments can be deposited slower than that. I don't think they can be deposited that slowly. That would be like a grain every day or something like that. The next thing we can do is look at the Bible, and the Bible seems to indicate that the deposition of layers took place very rapidly. In fact, a million times or 10 million times faster than the modern rate. So it's way over here somewhere, off the scale. And so if you believe in the biblical account of origins and that there is a short time involved in the history of the earth and then a global flood had a lot to do with it, then you're going to have rates that are very much faster than the rates we see today. The last thing we can do is look at modern sedimentation rates based on sedimentary processes. And when we do that, we get rates that are 2,000 to 10 million times faster than the rates determined by radiometric dating. In other words, how fast does this sediment have to be deposited to get the actual sedimentary features that we see in the fossil record? And we get rates that are a lot closer to our biblical model than they are to the radiometrically determined rates. So to summarize then, modern depositional rates are 1,000 times faster than the fossil rates calculated from radiometric dates. The biblical time frame gives us rates that are 10,000 times faster than that. And experimental sedimentation gives us a similar factor, so that sediment behavior is over here. Biblical based rates are there, modern rates are here, and radiometrically determined rates are over there. So it looks to me like something's got to be wrong with radiometric calculations. Well, this is not lost on sedimentologists. And over here at University of California, a sedimentologist by the name of Pete Sadler has made this one of his big studies, is to try to explain why it is that we get rates that are 1,000 times slower than modern rates. He doesn't understand the million times faster rate, so he takes the modern rates and says, why is it that the rates we see in the fossil record are 1,000 times slower than what we see today? And this is true throughout the Phanerozoic. And his conclusion is, well, there must have been a lot of erosion going on, and so you deposit stuff, and then you erode it, and then you deposit it again. And so it happens over and over again, so it looks like it's much slower than it is. This doesn't work. Doesn't meet the criteria that we see in the rocks, but that's what he has proposed. So that's the issue with respect to deposition. And it looks to me like perhaps this is a challenge to radiometric dating. All right, let's take another issue. Sediments don't appear in equilibrium with the environment. What do I mean by that? Well, let's take a look down here. This is our study area in the Colorado Plateau. Mostly up in this area here is where we work. And I'm going to give you a short course in geology that Dr. Brand suggested called breadimentology, where we actually use bread to represent sedimentary layers. And we can lay those layers one on top of another like this and get a pile of sediments. Those represent layers of rock. How would we know if there was significant time took place between this layer and the next layer up? What would you look for if that were the case? Well, let's take bread again. If that bread sits out there for a while, what's going to happen? Well, maybe it's going to mold. And Maybe there are even some rodents that might come along and nibble holes in it. Those are the kinds of things that might happen if time went by. So then the next layer is on top, and we have the other layers over that. How do we know that time has taken place between this layer and this layer? We look here and we see evidence of biological disturbance. Biological disturbance. So that tells us that a significant amount of time took place between this deposition and this one. Another thing that we could see that would identify that is if we had erosion take place and part of a layer was removed, and then the subsequent layers were conformed to that, and we get something like this. Now we can look back here and we can see, well, here's a layer that was one time deposited that now has been eroded away, and that requires some time, so there's got to be some break there in deposition. When we actually look at the rocks, what do we see? Well, in the vast majority of places we look, we see well-preserved sedimentary layers. We don't see any evidence of disruption. We see one layer after another stacked meter upon meter upon meter. Here, for example, is a piece of rock that shows a worm burrow right there. Very easy to see, but there's only one. What would time do? We would expect the sediments to be homogenized with time. All in the internal structure should be gone. There should be only the last episode of burrowing should show up, but that's it. The rest of it ought to look homogeneous. And so this condition is called homogenized. That's when burrowers have completely eliminated all the internal structure in the sediments. Typical rates given for sediment accumulation, we talked about this a minute ago, based on radiometric dates are 10 centimeters per 1,000 years, 1 to 10 centimeters per 1,000 years. That's a typical rate for sedimentary processes that's determined by radiometric dates. How fast do marine invertebrates burrow? Modern observed rates for homogenization, that is complete disruption of all the internal sedimentary structures, range from 1 month to one year in the modern sedimentary environment. But experimental rates go far beyond that, and we can disrupt 10 centimeters of sediment in just an hour, completely disrupt it and homogenize it if we have enough burrowers involved. And that takes about 10,000 burrowers. What is it, 1,000 or 10,000 per centimeter? 10,000 deposit feeders per square meter. That sounds like a lot, but some of these preapulid worms or siponid worms are up to 60,000 per square meter on the modern floor of the ocean. So there are lots of them around, and they would completely eliminate any internal sedimentary structures very quickly. At these rates, all sediment that we see in the fossil record, if you can disrupt the sediment in a year or less, completely homogenize it, and the depositional rate is 10 centimeters per 1,000 years, you can disrupt it 1,000 times or 1,000,000 times in the time available before it gets buried. We should see no sediments that are not homogenized anywhere. But instead we find that homogenized sediments are exceedingly rare. In fact, you have to make a pilgrimage to the sites that show homogenization in order to even find any. And this is a very unique situation. Richard Bromley, who wrote the textbook on bioturbation, the process of animals disrupting sediment, says 100% homogenization of the substrate is a natural product of the activity of the endobenthos, the burrowers. Failure to reach 100% or the failure of that state to be preserved in the fossil record are conditions that require explanation. So there's a lot of explanation required that hasn't been offered for why it is that the vast majority of sediments that we look at show all the internal structure they were deposited with. Going back down here to our research area, I'm going to show you some of the data. This is Dr. Brand and my work over a number of years. This is the diagrams I'm going to show you, and I'm not going to take time to allow you to walk through the whole diagram. I'll just show them to you quickly, so I'll explain what the diagram shows. Over here on the left-hand side, let me just advance that. Over on the left-hand side, you can see the geologic column, Paleozoic, Mesozoic, Cenozoic. These are the places in that record where we have found burrowing of any kind. Then here is the blow-up of the area concerned on this particular slide, which happens to be the Paleozoic. And this shows the actual geologic section that we measured. This tells how many meters of section we measured. And then over on this side, we have the results. Here's the scale. 1 means no burrows. That's right here on this side. 2 means some burrowing. 3 means significant burrowing and the beginning of disruption of the sediments. And 4 indicates homogenization. So this last column, anything that's in this last column is homogenization. Anything in this first column is essentially unburrowed. Any questions about that? Can you understand this? Look back at the diagram again. All right, we're going to go through some of these, and you can see what we're going to do is march up the geologic column starting here at the Paleozoic. We'll look at some sections here. This is the number of meters we measured. Now, measuring doesn't just mean taking a stick out there and measuring. It means looking at each layer that's exposed to see if there's any evidence of bioturbation over a section, an area wide enough for us to cover conveniently. So it means that we have looked at every single lamina in that section to see if we see any bioturbation. So here we see the Paleozoic section here. And these are the formations that we actually looked at. And in this area here, we found significant burrowing, but it's only at level 2, which means there are some burrows there. The vast majority of the sediments here and elsewhere that we measured are in column 1. All right, now we'll go on up to the Permian. And these are the formations in the Permian that we measured here. And that's 600 meters of sediment. And we found 2 layers here that had some burrowing in them. The rest of them didn't have any burrowing at all. So the vast majority of these are all in the column that requires an explanation for why they don't have any burrowing, according to Bromley. Now moving up into the Permian, upper Permian, we have the Kaibab Formation and White Rock, Cedar Mesa Sandstone, again, all in column 1. On up into the Mesozoic, we have the Triassic Moenkopi Formation and other formations. This is 550 meters of sediment we measured. It's all in column 1. There are a few cases of burrowing, but the vast majority of the sediments are not burrowed at all. We come up to the upper Triassic, the Chinle Formation, Shinnerup Conglomerate. And again, the question mark means we couldn't see the sediment. They were covered by, they either were not well exposed or we couldn't see what was going on. So the vast majority of this sediment is in column 1. The Jurassic, this is the Somerville Formation, about 60 meters, 55 meters, and we saw no sedimentary, no burrowing there at all. And the Morrison Formation, Cedar Mountain Formation, these are both in the upper Jurassic. We found 2 layers that had burrows in them, but the vast majority had no burrows, and one up there. Vast majority showed no burrowing at all, and none of it was significant. Then we came to the Cretaceous, Lower Cretaceous. Here we found a little bit more evidence of burrowing here and down here and up in here. And there were a few cases where there was significant burrowing and a couple of cases where we got complete homogenization. So that indicates that there was enough time between deposition of the layer below that and the layer above that for the sediment to be completely homogenized. So that means between an hour and a year, somewhere in that range. Going on up into the Upper Cretaceous, Blackhawk Formation. Again, we found a few occasions where there was significant burrowing. More burrowing as a general rule, but all of it's in column 1 except for these 5 points. Very small layers of sediment. Going into the uppermost Cretaceous, the Castlegate Sandstone, we found one place that had some burrows, but other than that, no burrowing. Bryce River Formation, that's 175 meters. And I throw out these 175 meters casually. You have to realize we're hanging on the edge of cliffs by our fingernails and looking for places to hold on as we climb these cliffs and examine this for burrows. We had to find the place with the best exposure, and usually that's a cliff. And so we did a lot of cliff climbing in this process. In fact, this is one of the places we climbed up right here. Fortunately, we had some women along so we could send them to do the hard parts. This is now in the Eocene, up in the Cenozoic. This is the Wasatch Formation. And we measured, I don't know how many meters, 500 meters of that. And where we could see the sediment, oftentimes you can't see it because it's covered or it's not, the face is washed and you can't make out what's there. The vast majority, all the ones we found were in column 1. And finally up here at the Green River Formation, we found whatever we could see of the Green River Formation showed no evidence of burrowing. So careful centimeter by centimeter analysis of thousands of meters of sediment across the Colorado Plateau showed a systematic and profound absence of features giving evidence for time. Looking for time in all the wrong places. The only reasonable way to preserve sedimentary features is by rapid sedimentation. So you have to cover the layer up before the benthos can get involved in burrowing. So you have to have sedimentation taking place exceedingly rapidly, one layer after another, in order to prevent burrowing to be effective. And since these sediments are covering a span of 500 million years, consideration should be given to the other interpretations of radioisotope ratios besides millions of years. Number 3, there's a general lack of erosion in the geologic record at places where it should be viewed. So we looked at bioturbation. Now we're going to look at erosion. And this is a talk we gave at Geological Society of America last year. And this indicates why we sometimes take our lives in our hands when we do this work. I'm standing on a contact right there, right where my feet are. I'm standing on Moenkopi Formation, and this is Shinneramp above me. And that gap, that line I'm walking on there, represents an absence of 10 to 35 million years. 10 to 35 million years when nothing happened. And so I challenged that at Geological Society of America a couple of years ago. This is where we got our data, a lot of data over a wide area. And here is the situation. You have the lower Triassic Moenkopi Formation, and then you have nothing deposited across the Colorado Plateau until the Chinle Formation up here with the basal Shinneramp. So there's anywhere between 10 and 35 million years of radiometric time that's displaced by that line. And here's what the line looks like over much of the area right here. It's perfectly flat. It's perfectly flat, and the layers along the contact can be traced for long distances. I'll show you right here, right over here is 20 kilometers that I'll show you the relationship of the parts. Here you can see layers like this one right here that go across that whole 20 kilometers. And that indicates that the erosion hasn't taken place. There's a little erosion at the top. There's some differences at the top. But the same level in the strata is still there. It's not been significant amounts of erosion during that 10 to 35 million radiometric years. There are some places where erosion shows up, like right here, but look at it. It's looking like this is depressed down into the underlying layers, and it's looking like it was not a hard rock. There's no steps along the edges of that area where there is erosion. However, there is something else that's very interesting. These are load casts. Here you see a load cast. A load cast is a structure that forms when the underlying material is unconsolidated, in fact is slurping mud, and the next layer that comes in pushes down into that layer and forms what's called a load cast. And this is a good example of one right here. Here are some other ones here. You can see where the Moenkopi Formation here has been displaced laterally by the impression of this overlying sandstone as it came in. We also found a layer of rock right here that is like porcelain. You can see a close-up of it right here. It's very, very fine grained. Here it is on the underside of one of the overlying rocks, and you can see where the overlying material pushed down through this layer. So these are load casts right here of Shinneramp that has pushed down through this porcelain that sits on top, porcelainite, which is a mud, very fine-grained mud. It has been displaced laterally by the overlying material. So these are examples of load casts. Here are some others. These are load casts here and here. This is the porcelainite here that has been squeezed up as these have pushed down around it. So we have something interesting going on here. We have a layer this big that covers quite a wide area, many kilometers. And that had to be there without being affected during the entire time that the Moenkopi was sitting there unmolested. It was still soft when the Shinneramp came on top. Clearly, the Moenkopi did not sit for 10 to 35 million years without erosion or deposition or lithification. Try to think of a model which would allow you to leave this sediment sit there for 10 to 35 million years. This is an isolated example. There are many other cases where there has been non-deposition for much bigger periods of time, and Grand Canyon is the largest of these with about 140 million years of time between the two layers. And yet the contact in most places in Grand Canyon is flat. There are a few places where there are erosive channels, but the vast majority of it is flat. These episodes of non-deposition are most readily explained by a model of rapid deposition and burial consistent with short time. Modern erosion rates on active margins of the continents are about a foot per year, and buying coastline property in California is a short-term proposition because every year the coastline is moving closer to Florida by about a foot. They give 1 million of those feet, and you're somewhere over in a lot closer to Florida than you are now. At this rate, California beaches will be in Florida in less than 15 million years. None of us probably would want to hang around for that time, but that's the modern rate of erosion of the coastline of California. Conservative and realistic rates of continental erosion based on modern erosion rates suggest all of North America will be eroded to sea level in 10 million years at current rates of erosion. Is it realistic then to say that these layers remain flat and undisturbed for 10 million years? Enough time for all of North America at current rates to be eroded down to sea level? It's not. Current erosion rates determined by a wide variety of indicators would have North America eroded to sea level 20 to 60 times in the 600 million radiometric years that life is supposed to have been on Earth. And yet, we see it's not even happened once because the entire geologic column is preserved in North America in various places. If all the layers of the Paleozoic have been laid down, and they were laid down 300 million years ago, then you've had enough time for 30 times North America to be eroded down, and all those sediments should be gone, and yet we find the complete geologic column in various places in North America. This hasn't happened even once. The presence of the geologic column in many places in North America and around the world gives evidence for this. This is most easily explained if we consider some other possible explanation for the lack of geologic time. So we've looked at rates of sedimentation. They tell us that the fossil rates determined by radiometric dating are not giving us anything like what we see today, and certainly nothing like what we would see if the biblical explanation of time was correct. We look at the general absence of bioturbation, and you say, why haven't other geologists caught on to this? Well, they aren't looking for it. And this is one of the things that Dr. Brand likes to emphasize, is that those people with a biblical model look for things that other people don't look for because they have reasons to look for them. And I think this gives you more freedom because you can see all the other things that other people see. Plus, you have the possibility of, because your model gives you more freedom, you have the possibility of looking at other things as well. And so if you believe the biblical explanation is correct, then the absence of bioturbation has some kind of a meaningful explanation, and that is that the radiometric dating is giving you a wrong answer. The absence of erosion. We don't see erosion in contacts that transit for many millions of years according to radiometric dates. How can that be true? What kind of an environment can you have where nothing happens? It's not that just the fact that they're not eroded is not a problem. They could be deposited on. So if you have continual deposition, that fills up the time. But you can't have nothing happening. Where on earth do you have nothing happening? Every place we know about is either being eroded or deposited. And over long periods of time, it's going to show. And yet here we're saying that this contact between those two units, nothing happened for 10 to 35 million years. That's not realistic. And finally, something that's come up just in the last decade or two is the question of biomolecules, the survival of biomolecules, far beyond what they should survive according to radiometric dating. And we're now getting stuff from scary down in the fossil record, way down, 250 million years ago, 300 million years ago. We're getting biomolecules out whose half-life at modern environments is a few thousand years. Where does this stop, and when do people begin to realize, whoa, this is lots of fun, sequencing these mammoths and sequencing Neanderthals. This is all lots of fun, but wait a minute now. What do we do about the time problem? So far what they've said is, that's interesting. Let's go back and look for some more. And they haven't really come to grips with the question of what it means. But ultimately, they're going to have to come to grips with it. I know Mary Schweitzer has been confronted with this many times. She's embarrassed by the things she's finding, and yet she's honest, and she wants to go ahead and discuss what she's found. But a lot of people are saying, shut up. And don't tell people what you're finding. Just keep it to yourself. But the fact is that we're finding biomolecules that are surviving far beyond where they should be. As a result of all these considerations, the meaning of radioisotope distributions ought to be, I think, reevaluated, because you can't reevaluate the meaning of 10,000 meters of sediment. That's fixed in stone. So something has to give. It doesn't indicate time, and yet we think there was a lot of time there if we follow the radiometric dating. So it suggests to us that something is wrong with radiometric dating. I am not a geophysicist. I'm not going to be able to solve that problem, but I wish somebody else would. Thank you.
Hi, Art. Not being a geologist, I need extra information, and I'm curious to see what causes bioturbation. Number one, what is an organisms? I like to know that. Number two, what do we know about hardening the rock formation? We visualize that sedimentation will be liquid mostly, in a liquid form. Gradients separate the various layers, but then eventually they end up as rocks, right?
Mm-hmm.
So what kind of process converts the liquid to rocks in such a, and what causes bioturbation? A little
Okay, let me
tutorial.
first address bioturbation. I should have done that during the talk. The most common bioturbators today and in the fossil record are believed to be marine worms of various types. And these worms burrow very fast. They don't survive at the surface very long because fish like to eat them. So as soon as you drop them on the surface, they're going to start burrowing. There also are shrimp that burrow and make burrows, and there are many other larger animals that also are burrowers. But the vast majority of the burrowers that we know about today are marine worms. And we think they were around in the fossil record. We know they were there because we find their burrows. And the fact that we find burrows occasionally means that we're not finding them the other time. If we never found any burrows, you might wonder if we could see one if it was there. But the fact that we find burrows means that there are other burrows, there are other places where there should have been lots of burrows, and they're not. The other question was, how do you make rock out of sediment? I'm inclined to think that most lithification takes place on burial. And the burial squeezes out water, and when the water leaves the rock, it takes minerals out, and those minerals get deposited. And sometimes the rock are cemented by just the grains being pressed together. Sometimes they're cemented by other minerals depositing in the rock, because after the rock's been deposited, then fluids can flow through the rock and leave deposits behind. And sometimes they're cemented that way. Or in limestone, in the case of limestones, they're cemented by precipitation of calcite, which is rock. So, but all those things are subjective. I know of one case where some experiments were done with sand, and the sand was being tested for porosity, which is what you do with sand when you're trying to find out whether there's room for oil in it. So a lot of labs that are studying oil samples, they test for porosity. And in this case, they had a chamber they could put the rock in, and they could pass fluids through it. And he was passing fluids through the rock, and overnight, all the pore space disappeared because it had precipitated out minerals in it. So it may not take very long to make a rock. Yeah.
Okay. I was just wondering, how much of these, how much level 4 turbation, what is it? Yeah, turbation, is like exists as far as on the Earth, like percentage-wise, or is it like less than 1%, or just to give a kind of total idea?
It's far, far less than 1%. It's about 0.01% of all the rocks we looked at in the Colorado Plateau. I also know that's true worldwide, because if homogenization was the rule, sedimentologists wouldn't have any work to do. They wouldn't be able to study the rocks to learn how they were deposited. And I know that to try to find some place where homogenization has happened, as I said, it's a pilgrimage. You have to learn first where it is, and then you have to drive there and look at that particular spot. We did find some, ironically, in the Navajo sandstone, which is supposed to be subaerial deposit, wind deposited sand, and we did find some beds there that were homogenized, completely homogenized, and that's a little interesting and unique. Don't know what that means.
So what is, well, my other question was, what is the deepest level for bioturbation that you've seen or know about?
Well, it goes all, even in our studies, it goes all the way back to lower Paleozoic. There's not much in the Cambrian, It's very hard to find in the Cambrian, in Ordovician, Silurian. It starts to pick up a little, and then Devonian on up. You do find it occasionally, but it's always rare. It's not,
Maybe I can follow that up with how much do you find of level 4 in the modern ocean bottom?
the places that have been studied show level 4 anytime there's enough rest time without deposition. So you get it in anywhere from a month to a year, you get level 4.
Also, since you said that it was marine worms primarily, again, you're talking about what, 60%, or just to get an idea of what exactly that means?
It
Or
depends on the
80%?
depth, and it depends on the
Area.
environment. Sometimes shrimp are the most common burrowers. But I think overall the marine worms are everywhere. And they probably are the most common burrowers.
Well, I'm assuming they're mostly in marine environments, not in the...
Yeah, I mean, if you have subaerial deposits, then it's gophers and plant roots and things like that that are bioturbating. So bioturbation is not limited to marine. And even in lakes, it also takes place. I don't know, Paul probably knows more about that than I do.
Just a couple of comments. When I lived in the ocean in Hydrolab, there was a big storm one night, and ripple marks formed all over the floor of the ocean. And it was interesting to me. By 3 days, they're all gone as a result of bioturbation. One word of caution I would suggest here is along the line of anoxic environments where you don't have organisms. You probably might take that into consideration in the equation. Further, in comment with your rate of erosion, it's a byproduct of your rate of erosion is that your ocean should be full of sediment. Of course, we don't have enough sediment on top, or continents on top to fill the oceans, but if the renewal model is there, you should have, and you can state, that the ocean should have been filled up at least 7 times over geologic time. That's a very conservative figure, incidentally. Now, the standard answer for that, of course, is trenches, where the sediments are drawn back into the earth. But calculations indicate that perhaps only about 10 to 20% of the volume of rivers reach the trenches and go down in the trenches. And we have a tremendous pattern of huge deltas around the Indus River, the Nile River, and so on, that tell us that, hey, these things have not been depositing that long. So there's a lot of data there of deposition in the ocean that I think you could add to your equation there.
I think about the anoxia, nobody is proposing that these sediments that I'm talking about here were anoxic when they were laid down. They are considered to be oxic environments. Shallow marine is most of them, and so that wouldn't be much of a challenge. Although there's some things you could talk about, like the Green River Formation, where you can make a case for that perhaps. But you do find occasional burrows even in those sediments. So whatever is going on, there isn't complete anoxia there. And if you have 1,000 years and there's incomplete anoxia, then sometimes burrowers are going to get down there and burrow.
Over here. Dr. Chadwick, you showed one slide that kind of piqued my curiosity. And at the bottom of the slide, there was a reference from the French sedimentologist, Guy Berthaud, who apparently worked with some Russian sedimentologists on a deposit in the St. Petersburg area. Mm-hmm. Now, you just slipped by that without any comment, but I noticed it, and Do you have anything more to add to that? Have you looked into that deposition and what it means with respect to deposition rates?
Well, that is the paper that gave me modern depositional rates of 20,000 to 10 million times in order to get the sediments deposited that they were studying in St. Petersburg. They had to deposit rates of deposition that were 20,000 to 10 million times faster than the radiometric dates would indicate. So that's the reference for that particular piece of data.
Was there any reference in that report that you may recall about such things as bioturbation and the things that...
I don't think they went that far. They were dealing with the sedimentation process itself.
We don't know much about sedimentation or lithification, which was inquired by our friend back here. Dr. Javor was his name.
Yes. Yes.
Any idea how long these bioturbators live?
I know their reproductive rate is very high. If you can have 60,000 bioturbators per square meter on the ocean floor, that wouldn't be very much fun to be down there on the bottom, I wouldn't think. But I suspect it's very high for those. The calcium acid shrimp, I think we probably have a better handle on that.
So what I'm thinking about is if you have one layer of all of that buried, where's the next layer of bioturbators going to come from? There must be some that have somehow escaped the burial to give the next generation a chance.
Well, that goes back to the rate of deposition, which is what this all comes down to. Is if you deposit another layer on top before that layer has time to be settled and colonized, then it's never going to be settled and colonized, and it's going to be protected. And so you bring another layer on that, another layer on that, and pretty soon you have your stack of sediments with no bioturbation. And that's the only explanation I can think of for how you could get tens of thousands of meters of sediment with no significant bioturbation. And occasionally you're going to get a worm brought in by the sediment. They certainly were in the original environment, so they're going to be brought in. And you can get bioturbation. If you bring in a lot of them, then you would get a lot of bioturbation in the first few seconds or minutes of, as I said, modern empirical studies, experimental studies have shown complete bioturbation down to 10 centimeters in an hour if you have 10,000 bioturbators. So it doesn't take very long for them to become active and to disrupt the sediments. So you really are at a loss. And I quote Richard Bromley again. If you're going to look at sediments that don't show any bioturbation, you better have an explanation for why. And that is the vast majority of the sediments in the fossil record.
What amazes me is what seems to be the tremendous violence that has to be involved in all this. And of course there was oh, okay. I believe you heard me. There's tremendous violence, and of course there's Mount St. Helens, and we can see what a small volcano does. But I mean, this has churned up more than a super galactic washing machine. It's just incredible. And so what are we looking at? 100,000 volcanoes at one time going off, or more, or less? And, I mean, I don't think anyone has any idea.
No, I
Something
think
has to be a source for all of this.
I think one of the weaknesses that creationists have to deal with, creationists means those of us who accept the biblical model and trying to grapple with the actual scientific data. One of the problems we have is not a good vision for what the world was like before the flood.
Yeah.
I think if we had some recognition of the conditions on the earth prior to the flood, it might make it easier for us to
But I don't think that's totally the
understand some
solution,
things.
because apparently this hit all the antediluvians with a great deal of surprise. And they didn't even have to see much
Well,
of what was going on, certainly not recorded.
Yeah, I'm just talking about the environments and the location
Yeah,
of things in
yeah.
the pre-flood world. It just
But
makes it very
I'm
difficult.
very amazed at all this. You know, it's just almost unimaginable.
Yeah. Any other questions?
If there aren't any further questions, I'll just make another comment. Mary Schweitzer, has come out with a paper recently that suggests maybe iron and chelation and hemoglobin added to blood vessels makes them last 2 years, compared to no hemoglobin, iron added, and so on. They disintegrate in a few days. She is cautiously suggesting that this may explain her 60 million year blood vessels in dinosaurs. Do you have any comments about that?
I think all the explanations are just mouths moving. I don't think there's anything significant coming out that's going to, and nor can it. I mean, we're talking here about physical processes that are as well understood or more or better understood than radiometric dating. We know how long these processes take place because we can do the experiments. We can study the thermodynamics of the breakdown of these bonds in various circumstances. We know about the Q10, and if we increase the rate of, increase the heat, we can multiply many times the speed with which these things break down. Those rates are all well known. The people that are arguing for an explanation for why these are so old, besides that they aren't, are really flapping their lips, trying to come up with something so far. Maybe somebody will find something, but if it happens for blood vessels, how does that help with bone proteins, or how does that help with DNA or RNA or whatever it is? How is that helping us sequence DNA from a Neanderthal, for example? It's so far not very much light. It just looks like they're in the same situation with regard to biomolecules that we are with respect to radiometric dating, maybe in worse shape. I don't have the answer on radiometric dating, but I have a lot of questions, and you've heard some of them today. So that's where I am.
I don't really have big questions or answers. I just have a comment on the attitude of the antediluvians, the people around Noah who were so confident there wouldn't be a flood. I'm not sure we really understand what was happening from what they say, because we look at how humans, how we can readily find explanations to explain away what we see happening. The earth in some places could have been falling apart, and a lot of things happening even before Noah, and the people would probably have some explanation, just like they're trying to explain how you get these ancient molecules. And they're confident that everything is fine, even though if they were open their eyes, they would realize it wasn't.
Good point.
I would add one comment here, and I think we probably should not say we don't have an explanation for radiometric dating without adding a few little comments. There are some radiometric dates that very much challenge the standard geologic timescale. I'm specifically speaking of residual carbon-14, and Paul Geem here right next to me knows a lot more about that. Some radiometric dates do challenge other radiometric dates, and there is a lot of examples of that, and I think that's part of the equation. We should not forget it.
Well, I think we have to all be prepared to live with uncertainty. We can't have all the answers to all the questions, or we'll have nothing to do in heaven. So I think it's, as scientists, we are prepared not to have all the answers, because that's what we do, is try to answer questions, and if there's no questions, we have nothing to work on. So I'm happy that we don't have all the answers. I'm happy to live with that uncertainty. I know it makes some people uncomfortable, but it doesn't bother me.
In the talk, you're talking about the Colorado Plateau. What makes that area so much unique that everyone tends to go towards that direction? Is it just because of the dry climate that things are more preserved? Why not other
Yeah.
areas?
Yeah, I think it's the lack of rainfall and the typical dryness that allows the rocks to be exposed. If there were better, if you've ever worked in the Appalachians or somewhere like that, you realize you just throw your hands up trying to see an outcrop. The only place you can work is the road cuts. And so they have a science called road cut geology where you go from road cut to road cut and study the rocks and then try to figure out what's going on in between. It's miserable. And in the Colorado Plateau, it's fun to work in geology. So yeah, that's why. Yes.
Welcome back, Art.
Thanks. Warren.
Anyone who's ever done field work in geology, and there are a number of people here, know how labor intensive it is. You and Leonard have done yeoman's duties in collecting the data, many hundreds of hours, I would think. Who knows how many? I don't know if you have a count on all the hours you spent, and we appreciate it. This is the kind of work that needs to be done from a creationist standpoint. Now, a lot of people may or may not know that you've done similar work, very labor intensive, with paleocurrents. I didn't hear the word paleocurrent at all during this presentation, but I'm sure there are reasons. What my question is, have you gone the next stage and take your data on paleocurrents and superimposed what you've done here in the Colorado Plateau? And what does it show about source areas for all of these vast thicknesses of sediments? And are the sources all eroded away? Have they disappeared? Or can we go upstream or out somewhere, and can we find remnants of where all these things came from? I think it would be a fascinating study.
Yeah, it would. I wasn't asked to talk on paleocurrents. I think Paul has already covered that, but I'm not sure. But that wasn't my topic, so I didn't discuss it. But yeah, I think any study like this can be interdigitated with the study of paleocurrents, and you can learn more. And so, sure.
Are you doing that now, or is that in the future?
Well, this next 2 months, I'm working on paleocurrents. Yes.
Okay. We want to see the latest results from that too.
Changing the topic. I'm sorry. All right. I had another question about layers, sedimentary layers. Are we able to go into the Precambrian region? And it's my impression there are no sedimentary layers there. Am I wrong?
Yes, you're wrong.
Okay. Okay.
The Precambrian rocks look just like Paleozoic rocks in every feature. You can find sandstones, siltstones, shales.
Well,
oftentimes they're metamorphosed more highly than the Paleozoic rocks, but there are all kinds of rocks.
But then we have now a question: how do sedimentary layers form in a antediluvian pre-flood Earth? Our picture of the pre-flood world is one of a stable, very idyllic place. Not quite Garden of Eden all over the world, but close to it. At least this is the Spirit of Prophecy's picture. And rocks are not exposed. Everything is covered, gentle hills, so on. In our current picture, there is no room for really large-scale sedimentation anywhere. And if there are, then what are we looking at?
I'm going to hazard my own opinion on this. I'm not going to try to defend it, but my opinion is that before God began his work of creation on this earth, it was covered by water, and there were winds moving to and fro, and there was deposition going on for eons. And that the earth itself, the physical part of the earth, was here, and sedimentation was taking place as it would today, as it is today.
If I may respond to that, Art.
Yeah.
This is, of course, one of the officially accepted position on in the Adventist community, but it flies in the face of the fourth commandment, where the Lord says in 6 days he created the heaven and the earth, and not just part of the earth, not the surface of the earth. So I have always been puzzled by how we get around that. And I feel more comfortable with the words etched in the stone.
Well, that's a theological issue. I'm not equipped to get into it, but I will tell you that why should God make only granite? Maybe he made some mudstone, siltstone, sandstone, shales, right? I mean, who says everything has to be granite when God made it? So if he made it, if you believe that, then it's possible God made those rocks. Yeah.
Okay, I was going to ask a question about the load casts. Now, those the load casts seem to be mostly kind of rounded, like an egg kind of shape, right? Because they're kind of squished in.
Yeah.
Because I don't know, I've seen some. There's quite a few rocks in the mountains over here that kind of are, but they're kind of sharded and shaled, so that's probably not this totally different thing. But I'm wondering about those load casts. I mean, do you ever wonder if those things are going to fall off, or, you know, because in the mountains here, it's kind of shardy kind of broken rock. I don't know what kind it is, but it's makes you wonder.
Yeah, I think load casts tell us that the material underneath that the coarse sediment was deposited on top of was very unconsolidated. It was so saturated with water that it couldn't hold up the sandstone that came in on top, and so it slurped down into the soft mud, and that's what a load cast is. So it's an indication of very rapid deposition on unconsolidated sediments. And I don't know how you do that with coarse, because the Shinrump is a very coarse conglomerate that the conventional wisdom says was deposited by a river, but a river can't come on top of a unconsolidated mudstone. It would erode it all away. So there's something wrong with that whole depositional picture. I didn't get into that.
Me? I guess it's my turn, is it?
Okay, Leonard, go ahead.
Go ahead, Leonard.
Oh, I just want to speak to Dr. Vor's question. I don't know the ancient biblical languages, but I've listened to some of our theologians who are, and they tell us that the some of these terms, like for heavens and the earth in the creation story, the original words can have various meanings. You can speak about the heavens, way up the starry heavens. You speak about the heavens in the sense of where the birds fly, the earth as the whole earth, or the earth as where the worms crawl. And that in Genesis there, it's talking about where the birds fly and where the worms crawl. So it's not really talking about, and it's not saying that he created the heavens, the whole universe and the earth in our 7-day creation week.
Adding to that discussion, this is, of course, something that's been discussed for years and years in the Adventist Church, and there's the question, was there matter here at the earth before creation week, an empty earth here? A Review and Herald in 1860, editorial there suggests there's nothing in the Bible against that idea. Folks, this is way back in our history. There are some people who say, hey, the Adventist Church has changed its view now. It talks about an older earth. It didn't used to talk about that. It's been with us from the beginning. F.M. Wilcox in the 1890s, 80s, and there he was editor of the Review. He also suggests the same thing. This tends to be a major difference between us and the traditional creation groups, ICR, Creation Research Society, Creation Answers in Genesis, and the group in Australia and so on. These all believe that the whole universe is only about 6,000 years old. Adventists tend to lean away from that idea, although many of us don't. But in support of this, I would say that there are suggestions. I believe those who authors in the workers in the Bible did believe that there was something here before. Genesis, God's creative acts don't start till after an empty earth is described. That's one point. You get to 2 Peter 3, verse 5, it says the earth created out of water. You go to Psalms, I believe it's 24:2. It talks about earth being formed out of water. And you go to Psalms 136:6, same thing. I believe the people who wrote the Bible were of the idea that there was something here before.
Like your comment there. One of the things I think is contradictory among ourselves is some of us say that the earth as a mass, perhaps, was here for a very long time, before the creation of life. Some say that on the fourth day God created the universe. Well, it took 7 days to create life on this planet, and it took only 1 day to create the universe. And there's other such bits of confusion in all this. God's eternal. What was he doing? Twirling his thumbs for 100 trillion years and decided to create the earth, and then while he was midway through the creation, he thought, oh, it would be nice to have a universe. I mean, I just don't think that makes much sense.
I think we need to be very careful because we're far afield from my presentation. It's beginning to sound like letters to the editor and Spectrum.
But we were getting kind of into this, so I just thought I'd bring it up.
I don't want to spend my time talking about something I don't know anything about.
Can you relate any of this stuff to the amount of water flow it takes to produce sandstone or conglomerate? It seems that you have to have water flow at a certain speed, or otherwise you can't keep the particles in suspension.
Yeah, that's what this paper that Bernard was asking about is about. You have to have deposition at this rate in order to get this kind of sediment deposited in this environment. So those kinds of studies give us rates infinitely faster than what we get from the modern environment, or because we're not depositing those sediments today. When we're depositing in depositional environments today, it's mostly mud that's carried by the water, either as turbid mud flows or sediment, suspended sediment that's flocculated out in situ.
I was just curious, what could a person date the Earth if the only information they had was how much erosion had taken place? What?
That's a good question. Because rates can be variable to infinity, you can't really do that either with deposition or erosion. You couldn't use those as metrics, but you can use them as limiting metrics because you can't have zero erosion or zero deposition, and if you have very slow deposition, you ought to have a lot of bioturbation. You ought to lose all your internal sedimentary structure.
Well, it seems like to me if you're just basing it on you said 20 to 60 times it would be eroded to the, seems like you could do it mathematically at least.
Oh yeah, there is a modern erosional rate based on all the sediment going to all the rivers that's delivered to the oceans.
It's an average.
Yeah, you can walk back from that to how long it'd take at that rate to get rid of everything above sea level. And that's where they get the 10 million year figure.
Does the mud flow at Mount St. Helens give us any information on some of these mud flow?
No, I haven't studied that. There were some mud flows that were very deep and very fast, infinite. Well, not infinite, I don't want to use that word. But they deposited very quickly and they deposited very thickly. So yeah, there was some sorting that took place in those. And some of those were subaqueous and some were subaerial.
Question on erosion rates versus plate movements. We can see obviously all these mountains that are around us, and the excuse for the formation of mountains is plates moving, colliding, and volcanoes and whatnot that would build things up. But at the same time, erosion has taken place, and so you have a little of that deteriorating, and then you've got something building up. But when we see these pictures of all of the sedimentary layers, they're all relatively flat, with some exceptions of where movement may have tilted it to its side, but even then the layers are relatively flat. How do you explain that, or what is the reason for that? If we have so much movement going on, how is it that the layers are all flat or relatively flat?
One of the principal rules of geology in sedimentology and stratigraphy is that layers are deposited flat because they're in water, and that's what happens. Sediments settle out flat if you drop them into water. There are, of course, if you're on the slopes of a volcano and you're depositing something, eventually it's going to be redeposited somewhere else in water, and that's going to end up in a flat layer. So I think that rule is pretty well adhered to in geology, and if you find layers that are not flat, you better have an explanation for why they're not. It has to do with maybe butting up against something that was subsequently buried, but typically geologists assume if you have a flat layer, that's in position.
So we see, following up on that, we see all that all over the world.
Yeah.
So that would indicate that these layers were all under some form of water.
Presumably that's the case, yeah. Now some layers are not flat, and one kind of layer that's not particularly flat is sand dunes, where the top slopes may be tilted some way or other because they're eroded by wind, modern dunes. But if it's deposited in water by the processes we know work in water, traction processes and so on, suspension processes, they're going to end up being flat. And by the way, since you brought it up, if you raise an area like the Rocky Mountains or something like that, you increase the erosion rates greatly. The higher the relief, the faster the erosion rates. And so you can imagine that if time had been here long enough to erode the mountains, there'd still be mountains there, but they wouldn't have the layers of sediment that were deposited on top of them still there. The fact that we find sediments all over North America, all over the world, that are still there means that there hasn't been time.
We were told there at Red Rocks that the rocks we saw were a second uplift, that there had been Rocky Mountains previous that had eroded away. What's the evidence for that?
There are beliefs, commonly believed to be two episodes of Rocky Mountain uplift, and what they call the ancestral Rocky Mountains and the current Rocky Mountains. The evidence is based on the geography that would be produced if they were there, why you have sediment suddenly going away from this area. That would indicate a high there. And I don't know all the data. There may be some radiometric dates in that as well. But it is a widely believed thing that there were two episodes of Rocky Mountain uplift.
Well, another thing seems to suggest incredible, almost unbelievable amount of violence in what has happened in the past. Is that, if I'm correct, I believe top 4,000 feet of Mount Everest is clamshells, which of course is off the ocean bottom. And to get them, almost 30,000 feet in the air or whatever it is. And I understand most of those shells are closed, which means the clams were still alive. I think when a clam dies, it opens up. So releases probably when instead it releases the tension it normally would have when it's alive to keep the shell closed. So it must have really happened fast, very quickly.
I don't know.
That's a common argument for rapid deposition. We've seen this quite dramatically in the Alps. So many of those clams are shut. And it means they didn't die a normal death. And I might just add another comment about these rates of erosion. Some people argue, well, our present rates are way too fast because there's so much agriculture. And you need to take that into account in your rates. There are good scientific estimates of this. Used to be maybe agriculture has doubled the rates of erosion, which of course does nothing for the argument because the rates are so much faster. I mean, cut the figures in half, still a huge problem. But added to that, more recent paper says, well, unfortunately, a number of these rates of erosion are based on erosion from farm areas and so on that are not near the ocean. Hence, those sediments are not recycled into the ocean. They're recycled into the continents again, and the rates involve a considerable amount of recycling on the continents, which reduces the figure. And I think you can safely state erosion, farming at least, probably only increases rates of erosion by a quarter, at best a third.
I want to thank you very much, Dr. Chadwick, for coming and giving us your talk. Very much appreciate hearing what you had to say.
Thank you.